take a slow breath in and gently let it out. Welcome back to Science Sleep. This channel is a place where curiosity slows down, where big questions are explored calmly, and where science becomes something you can rest your mind inside. If you enjoy thoughtful, educational content designed for sleep, consider subscribing to the channel. And as you listen tonight, leave a comment sharing what you think about this idea. Do you believe the universe could be a simulation or not? Now, get comfortable. Let your breathing become steady. There is nothing you need to do, nowhere you need to go. Tonight's question is simple and very old. What if the universe is a simulation? And what does modern physics actually say about it? This is not science fiction. It is not a movie plot. It is a serious question discussed quietly by physicists, cosmologists, and philosophers who study the deepest structure of reality itself. We begin at the beginning. For most of human history, the universe was assumed to be exactly what it appears to be: solid, continuous, objective. A vast stage where matter moves through space and time. But in the last 100 years, physics has slowly revealed something unexpected. Reality is not solid. It is not continuous, and it may not even exist independently of observation. The idea that the universe could be a simulation did not begin with computers. It began when physics discovered that reality behaves less like a solid object and more like information. In the early 20th century, classical physics began to fail. Newton's laws worked well for everyday objects. But when scientists looked closely at very small things, atoms, electrons, photons, the rules changed. Energy came in packets. Particles behaved like waves, and outcomes could only be predicted as probabilities. This was the birth of quantum mechanics. One of the strangest discoveries was that particles do not have definite properties until they are measured. An electron does not have a single position. It exists as a cloud of possibilities. Only when measured does one possibility become real. This is known as the observer effect, and it has been confirmed repeatedly with extraordinary precision. In a simulated world, this behavior would make sense. In computer simulations, details are often rendered only when needed. There is no reason to calculate unnecessary information. Resolution appears only where attention is focused. Physics shows us something similar. At the smallest measurable scales, reality seems to conserve information. Nothing is fully defined until it must be. Now let us step back and look at the universe as a whole. Space and time feel smooth and continuous, but when measured carefully, they appear to be quantized. There is a smallest possible length, called the Planck length. There is a smallest possible unit of time, called the Planck time. Below these scales, the concepts of space and time stop making sense. This is not speculation. These limits arise naturally from combining quantum mechanics with general relativity. In other words, the universe has a maximum resolution, just like a digital image. If you zoom in far enough on a digital photograph, you eventually reach pixels. There is no further detail beyond that point. Physics suggests the universe behaves the same way. Now consider speed. There is a maximum speed in the universe. Nothing can travel faster than the speed of light. This is not just a speed limit for objects. It is a limit on how fast information can travel. From a computational perspective, this looks like a processing constraint, a maximum bandwidth, a universal clock rate. Einstein showed that time itself slows down as objects move faster. Clocks tick at different rates, depending on motion and gravity. Time is not absolute. It is calculated locally. Again, this matches what we would expect in a simulated environment, where time is not fundamental, but emerges from processing steps. Now we arrive at a key question. Why would physicists even consider the idea that the universe is a simulation? The most well-known modern formulation comes from philosopher Nick Bostrom. His argument is not emotional or mystical. It is statistical. In short, it states this: if intelligent civilizations tend to survive long enough to develop advanced computing, and if they are interested in simulating realities, then simulated universes would vastly outnumber base, original realities. If even a small fraction of civilizations run many simulations, then statistically, most conscious beings would exist inside simulations. This does not prove we are in a simulation, but it does change the odds. Physicists became interested not because of philosophy, but because the universe already behaves like something computational. The laws of physics are described by mathematical equations that are astonishingly precise. Reality follows mathematical rules, with no exceptions ever observed. Electrons are identical everywhere. Physical constants do not vary randomly. The universe runs on stable parameters that look very much like fixed values in a program. Some physicists have even described the universe as a quantum information processor. In this view, particles are not tiny objects, but packets of information. Forces are exchanges of data. Space is a network. Time is an update sequence. If this sounds abstract, that's because it is. But abstraction is where physics lives. Now consider black holes. Black holes do something remarkable. They store information on their surfaces, not in their volume. This discovery is known as the holographic principle. It suggests that all the information inside a region of space can be described by data on its boundary. Our three-dimensional universe may be encoded on a two-dimensional surface. This is not metaphor. It arises directly from equations tested through observation. Holographic universe is deeply compatible with the idea of simulation. It means reality is not what it appears to be. Depth is an illusion. Volume is emergent, just like a 3D video game world, rendered from underlying data. Now let us slow down even further. Take another breath. At this point, some people feel uneasy. If the universe is a simulation, does that mean nothing is real? Physics gives a calm answer. Reality does not disappear just because it is computed. Pain still hurts. Joy still matters. Cause and effect still apply. Hurricane still destroys a simulated city. A simulated star still burns for billions of years. The word simulation does not mean fake. It means implemented, just as a song stored as data is still real music when played. Now we turn to consciousness. This is where physics becomes quiet. No current theory explains why subjective experience exists. We can describe neurons. We can model brain activity. But the fact that there is something it feels like to be you remains unexplained. Some scientists speculate that consciousness is fundamental. Others suggest it emerges from information processing. If consciousness arises from computation, then a simulated brain could host a real mind. This is uncomfortable, but it follows logically. The universe does not grant meaning. We do. Whether base reality or simulation, the experience of being alive remains the same. Now let us ask the final scientific question. Is there evidence we are in a simulation? At present, there is no direct proof. No visible pixels in the sky. No hidden error messages in physics. But scientists have proposed tests. Some suggest looking for anisotropies in space-time at extremely high energies. Others examine whether physical constants appear finely tuned for computational efficiency. So far, nature remains silent, and that silence is meaningful. If the universe is a simulation, it is an extraordinarily consistent one. No shortcuts, no glitches, no narrative convenience, just laws. Quiet, relentless laws, and perhaps that is the most calming thought of all. Whether simulated or not, the universe is stable, predictable, mathematical. Stars will rise, atoms will bond. Time will flow forward. You are safe inside these rules. As you rest now, let the question drift gently. What if the universe is a simulation? Not as a fear, but as a reminder that reality is deeper and more mysterious than it appears. And that mystery has room for wonder and for sleep. Take one more slow breath in and let it go. When you're ready, you may drift further down into rest. There is no rush to understand everything. Understanding can come later. For now, we simply observe the ideas, the way physicists observe the universe itself. Quietly, patiently, without forcing conclusions. Let us return to the foundations of physics and look more carefully at what reality is made of. For centuries, matter was thought to be fundamental. Tiny, solid pieces, bouncing and colliding in space. But modern physics tells a different story. At the deepest level we can measure, matter dissolves into fields. An electron is not a tiny marble. It is a vibration in an electron field. A photon is a ripple in an electromagnetic field. Every particle in the universe is an excitation of an underlying field that exists everywhere. This means empty space is not truly empty. Even in complete vacuum, fields fluctuate. Particles briefly appear and disappear. Energy flickers in and out of existence. From a computational perspective, this resembles a background process, a constant baseline of activity beneath visible reality. Now consider how these fields interact. The interactions are governed by simple, elegant equations. They are local, rule-based, and deterministic at the level of probabilities. This is exactly how simulations operate. Rules are applied locally. States update step by step. Global behavior emerges from simple interactions. Nothing in physics requires continuous infinity. In fact, infinity causes problems. When equations predict infinite values, physicists know something is wrong. Renormalization exists to remove infinities and keep calculations finite. Nature seems to prefer limits, maximum speed, minimum length, discrete energy levels. These are not arbitrary. They are signatures of a universe that is constrained. Now let us gently examine space itself. We tend to imagine space as a passive container in which things happen. But general relativity tells us space is active. It stretches, it curves, it responds to energy and mass. Gravity is not a force. In the traditional sense, it is geometry. Objects follow the shape of space-time, the way water follows a riverbed. This geometry can be calculated, predicted, simulated. In fact, physicists routinely simulate space-time. On computers, they model black hole mergers, gravitational waves, the evolution of the early universe, and remarkably, the simulations match observations. This does not mean the universe is a simulation, but it does mean the universe behaves like something that can be simulated with extraordinary accuracy. Now let us move to the very beginning, the Big Bang. The universe began, not as an explosion in space, but as an expansion of space itself. At the earliest moments, the universe was extremely simple, uniform, hot, dense. As it expanded, small fluctuations grew. These became galaxies, stars, and eventually planets. The initial conditions of the universe were incredibly precise. If certain constants were slightly different, the universe would not form complex structures. no atoms, no chemistry, no life. This is known as fine-tuning. There are several explanations. One is necessity. The constants could not be otherwise. Another is chance. We happen to be lucky. A third is the multiverse. Many universes exist, and we observe one compatible with life. A fourth is design, and quietly, some consider a fifth possibility, that the universe was configured. Again, this does not prove a simulation, but it aligns with the idea that the universe is not random chaos, but structured from the start. Now we turn to information. In physics, information is not abstract. It is physical. Landauer's principle shows that erasing information requires energy. Information has weight, cost, consequences. Black holes obey information laws. Quantum systems preserve information. The universe never forgets. This has led some physicists to suggest that information is more fundamental than matter or energy. That reality is, at its core, made of bits, or more precisely, quantum bits. If this is true, then the universe resembles a vast quantum computation, not running on a computer inside the universe, but being the computation itself. This idea dissolves the sharp boundary between simulated and real, because if reality is computation, then computation is reality. Now let us return to the speed of light. The speed of light is the same for all observers. No matter how fast you move, light still travels at the same speed relative to you. This strange fact forces time and space to adjust. Lengths contract. Clocks slow down. These effects are not illusions. They are measured. Why does the universe behave this way? One interpretation is that the speed of light is the maximum update rate. For causal influence, nothing can change faster than information can propagate. This is exactly what we would expect in a system with limited bandwidth. Now pause for a moment. Let your shoulders relax. Let your thoughts drift slowly. We are not building an argument. We are exploring patterns, and the patterns are consistent. Now consider randomness. Quantum mechanics includes genuine randomness. Outcomes are not determined until measured. Some find this incompatible with simulation, but simulations can include randomness. True randomness can be sourced externally or effectively generated internally. And importantly, quantum randomness is constrained. It follows strict statistical rules. It is not chaotic. It is regulated uncertainty. Now let us talk about emergence. In complex systems, simple rules can generate unexpected behavior. Consciousness may be emergent. Life certainly is. No single molecule is alive. Life emerges from interactions. Similarly, space and time themselves may be emergent. Some theories suggest space is not fundamental, but arises from entanglement. Entanglement is a quantum connection between particles that persists across distance. When systems are entangled, they behave as one, even when separated. Space may be a consequence of these relationships. If space emerges from information, then the universe is not built from space. Space is built from something else, and that something else looks very much like data. Now let us gently address a concern. If the universe is a simulation, who is running it? Physics does not answer this. Physics only describes behavior. The simulation hypothesis does not require a human-like simulator. It does not require intention. It only suggests that reality could be implemented on a deeper layer, just as atoms implement chemistry and chemistry implements biology. Each level emerges from the one below. A simulated universe would simply be another level. Now rest with that thought. There is no implication that you are watched, no implication that meaning is removed. If anything, meaning becomes rarer. A conscious moment in a vast computational universe is precious. Now we come to a quiet truth. Science does not care whether the universe is a simulation. The equations work either way. Predictions remain the same. Experiments yield the same results. This is why physicists discuss the idea calmly, not because it changes daily life, but because it reveals how strange reality already is. The universe is not intuitive. It never was. And yet, it is beautifully consistent. Now, let us slow further. As your mind settles, consider this final reflection. If the universe is a simulation, then curiosity is part of the code, because you exist, and you ask questions. And that means the universe, whatever its nature, supports awareness, supports thought, supports wonder, and that is enough. Let the ideas fade gently now. They do not need resolution. The universe continues, whether watched or not. Stars burn quietly. Fields fluctuate softly. Time advances one step at a time. And you can rest inside this vast, orderly mystery. Breathe in and out. And when you are ready, sleep can take over, carrying these thoughts away like distant stars, slowly passing through the night. The simulation hypothesis asks a specific question. Is the physical universe best described as a fundamental reality or as an implemented one? Physics does not use the word simulation casually. In this context, it means that the laws of nature could be the result of underlying computational rules rather than irreducible facts. This idea emerges naturally from three discoveries in modern physics. First, reality is discrete, not continuous. At small scales, energy comes in quanta. Electrons occupy fixed energy levels. Space and time appear to have minimum measurable units. There is no evidence for infinite resolution in nature. If the universe were continuous all the way down, physics would allow arbitrarily small measurements. It does not. Instead, below the Planck scale, current theories break down. This suggests a fundamental limit to resolution, consistent with a digital structure. Second, the universe obeys strict information limits. The speed of light is not simply the speed of photons. It is the maximum speed at which information can propagate. No signal, interaction, or causal influence exceeds it. This imposes a global constraint on how fast the universe can update. In computational terms, it functions as a clock speed. Additionally, black holes place upper limits on information density. There is a maximum amount of information that can be stored in a region of space. This limit scales with surface area, not volume. That is the holographic principle. All physical systems respect this bound. The universe never exceeds its informational capacity. Third, physical laws are algorithmic. The equations of physics are local. They evolve states forward in time. They depend only on neighboring values. This is exactly how computational systems operate. Quantum field theory, the most accurate theory ever developed, treats particles as excitations of fields governed by update rules. Nothing moves freely. Everything updates according to constraints. From these three facts alone, the idea that the universe is computational is not speculative. It is descriptive. Now consider the observer problem in quantum mechanics. Before measurement, quantum systems exist in superpositions. They do not have definite outcomes. After measurement, one outcome appears. This is not a limitation of instruments. It is a fundamental feature of nature. The wave function does not represent ignorance. It represents real indeterminacy. This means the universe does not fully specify reality everywhere at all times. In computational systems, this is called lazy evaluation. States are not resolved until required. Physics exhibits this exact behavior. Now consider fine-tuning. The constants of nature fall within narrow ranges that permit structure. Small deviations prevent galaxy formation, nuclear stability, or chemistry. Physics offers no internal explanation for these values. Simulation does not explain them either, but it reframes the question. Constants become parameters, not necessities. This is why physicists consider the hypothesis seriously. It aligns with known features of the universe without contradicting them. Next, consider consciousness. Physics does not explain why subjective experience exists. However, neuroscience shows that mental states correlate with information processing. If consciousness arises from computation, then substrate does not matter. A simulated brain running the same processes would produce the same experiences. This does not require mysticism. It follows from functional equivalence. Now address the common objection. Simulation means fake. This is incorrect. If a system obeys consistent laws, supports causal structure, and contains conscious observers, it is real in every physically meaningful sense. A simulated star emits real simulated light. A simulated organism experiences real simulated pain. Reality is defined by internal coherence, not by substrate. Now ask the critical question: can physics detect a simulation? At present, no. Any sufficiently advanced simulation would reproduce physical laws exactly. There is no requirement for glitches, pixels, or boundaries. Physics can only test internal consistency. And so far, the universe passes every test. The simulation hypothesis is therefore unfalsifiable with current methods. That does not make it unscientific. It makes it metaphysical, constrained by physics. Now, here is the most important point. Whether the universe is simulated or fundamental does not change physics. The equations remain the same. Predictions remain the same. Experiments remain valid. Physics describes behavior, not origin. And behavior is all that science requires. The universe operates as if it is rule-based, information-limited, and computational. That is the conclusion. Not that we are in a simulation, but that if we were, physics would look exactly like this. And that tells us something important. The deepest layer of reality is not matter. It is structure, rules, constraints, information. And whatever exists beneath those rules is irrelevant to how the universe functions. That is what physics actually says. Now we push the analysis further and remove ambiguity. The simulation hypothesis stands or falls on one question. Is the universe better described as fundamentally physical or fundamentally informational? Modern physics increasingly favors the second description. Start with quantum mechanics. Every physical system is described by a wave function. The wave function does not describe objects directly. It encodes information about possible outcomes. Measurement updates information. It does not reveal pre-existing hidden values. Bell's theorem proves this. Experiments violate Bell inequalities, meaning reality cannot be explained by local hidden variables. The universe is not secretly classical underneath. This is not interpretation. It is experimental fact. What exists fundamentally are correlations, probabilities, and constraints. Now look at quantum field theory. Particles are not entities moving through space. They are excitations of fields defined at every point. Fields themselves are mathematical objects. They evolve according to equations. There is no evidence of substance beyond the equations. This leads to a critical conclusion. Physics does not describe stuff, it describes behavior. If reality is behavior governed by rules, then implementation becomes an open question. Now consider space-time. General relativity treats space-time as dynamic. Quantum gravity attempts to quantize it. Leading approaches, loop quantum gravity, causal sets, spin networks, ADS-CFT, do not treat space-time as fundamental. They treat it as emergent. Space-time arises from discrete structures and relationships. Causal set theory models space-time as a network of events. Spin networks model it as graphs with quantized geometry. Holography encodes volume in boundary data. These are not metaphors. They are mathematical frameworks. In every case, continuity disappears. What replaces it are nodes, links, updates, and constraints. These are computational primitives. Now address entropy. The second law of thermodynamics states that entropy increases. Entropy is a measure of information. More precisely, it measures the number of microstates compatible with a macrostate. Time's arrow is informational. The universe evolves toward states of higher informational disorder. This suggests that time itself may be a bookkeeping process, an ordering of state updates. In computation, time is exactly this, a sequence of state transitions. Now examine the limits. The universe has a finite age, a finite speed of information, a finite entropy bound. These are not features of an infinite, unbounded continuum. They are features of a finite system. Now address the strongest objection. Computers exist inside the universe, so the universe cannot be a computation. This is a category error. Biology exists inside chemistry, yet biology is implemented by chemistry. Chemistry exists inside physics, yet chemistry is implemented by physics. Higher-level processes do not negate lower-level implementation. A computation does not need to resemble a laptop. It only needs rule-based state evolution. The universe qualifies. Now ask whether simulation implies purpose. Physics says nothing about purpose. A simulation could exist for study, curiosity, accident, or no reason at all. The hypothesis does not smuggle in theology. It only replaces one unexplained foundation with another. Instead of asking, why do these laws exist? We ask, why these rules? Both questions are equally unanswered. Now consider empirical proposals. Some physicists have suggested searching for preferred reference frames, lattice anisotropies, or energy cutoffs inconsistent with Lorentz invariance. So far, none have been observed, but absence of evidence is expected. Any simulation capable of producing our universe would be extraordinarily precise. Now address meaning. If the universe is simulated, meaning does not evaporate. Meaning is not supplied by fundamental ontology. It emerges from conscious systems valuing outcomes. That remains unchanged. A simulated joy is joy. A simulated loss is loss. Physics cannot erase that. Now we reach the actual scientific conclusion. The simulation hypothesis is compatible with modern physics. It is not required by physics. It is not disproven by physics. It is a plausible metaphysical interpretation of known facts. And here is the critical distinction. Physics tells us how the universe behaves. It does not tell us what ultimately exists. That gap is unavoidable. Every physical theory assumes a foundation it does not explain. Simulation theory simply relocates that foundation. Now the final point and the most important one. If tomorrow we proved the universe is a simulation, physics would not change. The standard model would still work. General relativity would still work. Experiments would still yield the same results. The universe would not glitch. Time would not stop. The reason is simple. Physics is about internal consistency, and the universe, simulated or not, is internally consistent. That is the end of what physics can say. Everything beyond that is interpretation. The universe runs on rules. Those rules are stable, and they are sufficient. That is the scientific position. Now we address why, despite all of this, most physicists remain agnostic about the simulation hypothesis. The reason is not skepticism or dismissal. It is methodological restraint. Science advances by testing predictions. A hypothesis must, in principle, be falsifiable. At present, the simulation hypothesis does not make unique testable predictions that differ from standard physics. Any observation consistent with a simulated universe is also consistent with a non-simulated one. This places the idea outside experimental science, at least for now. That does not make it meaningless. It places it in the category of foundational interpretation. Physics has many such interpretations. Is the wave function real or epistemic? Do many worlds exist? Is time fundamental or emergent? These questions are debated, not measured. The simulation hypothesis belongs to this group. Now consider the argument from probability. Nick Bostrom's reasoning is often misunderstood. It does not say we are likely in a simulation because simulations are easy. It says that if advanced civilizations tend to run many simulations, then simulated observers would outnumber original ones. This is a conditional statement, not a prediction. Each premise may be false. Civilizations may self-destruct. They may lose interest in simulations. Consciousness may not arise in simulated systems. Any of these invalidate the conclusion. Physics does not weigh in on these premises. Now examine resource constraints. Simulating a universe at full resolution would require enormous computational power. However, full resolution may not be necessary. Only local regions require detailed calculation. Distant galaxies need only obey large-scale statistics. Quantum uncertainty already limits precision. This again mirrors computational optimization. But optimization does not imply simulation. It implies efficiency. And efficiency is a common feature of physical laws. Now address cosmology. Inflation theory explains the large-scale uniformity of the universe. It predicts patterns in the cosmic microwave background. These predictions have been confirmed. No anomalies currently require a simulation explanation. The universe behaves exactly as expected from known physics. This strengthens agnosticism. There is no pressure to invoke additional layers. Now consider ethics. Some worry that simulation implies disposability. Physics does not support this concern. Moral value does not derive from ontological depth. It derives from experience. Physics is silent on ethics. Now the final boundary. No scientific theory can explain why there is something rather than nothing. Simulation does not answer this. It only postpones it. Why does the simulator exist? Why do its laws exist? The regress does not end. Physics always terminates at axioms. The universe has rules because those are the rules. Now summarize the position cleanly. Physics supports the following statements. Reality is quantized. Information is fundamental. Space-time may be emergent. Physical laws are algorithmic. The universe has finite limits. From these, simulation is a coherent possibility. Physics does not support these statements, that we are definitely in a simulation, that simulators are watching us, that reality is illusory or meaningless, that physics is incomplete because of simulation. Those are not scientific claims. Now, the closing scientific conclusion. The simulation hypothesis is not a revolution, it is a reframing. It asks whether the universe is the base layer of reality or a higher-level process. Physics cannot currently distinguish between these options. And that is not a failure. It is a reminder of what science is. Science maps behavior. It does not reveal ultimate origin. And the map we have is extraordinarily accurate. Whether written in fundamental reality or executed as code, the universe obeys the same laws. Long before computers existed, some physicists suspected that mathematics, not matter, was the deepest layer of reality. Galileo wrote that the universe is written in the language of mathematics. Einstein believed that physical reality is structured by mathematical necessity. Dirac argued that equations are more fundamental than interpretation. This was not philosophical decoration. It came from experience. Again and again, equations predicted phenomena before they were observed. Antimatter, gravitational waves, quantum tunneling. Reality followed mathematics, not the other way around. This led to a radical proposal in modern physics, the mathematical universe hypothesis. It suggests that physical reality is a mathematical structure, not described by mathematics, but identical to it. If this is true, then implementation is irrelevant. A mathematical structure exists whether it is computed or not. Simulation becomes a special case of a deeper idea. That reality is formal. This is why many physicists are indifferent to the simulation question. To them, it changes nothing operational. Now consider digital physics. Digital physics proposes that the universe evolves in discrete steps. Cellular automata are often used as models. Simple local rules generate complex global behavior. Stephen Wolfram and others explored whether space-time itself could emerge from such systems. These models reproduce many qualitative features of physics, but they also face challenges. Lorentz invariance, a cornerstone of relativity, is difficult to reproduce in discrete lattices. So far, no digital model reproduces all known physics exactly. This, again, supports agnosticism. Now address the relationship between simulation and many worlds. The many worlds interpretation of quantum mechanics says that all possible outcomes occur. There is no collapse, only branching. In such a universe, computation is cheap. Simulating all branches may be more natural than selecting one. This is one reason simulation is often discussed alongside many worlds. But this is interpretive, not required. Now return to empirical science. Every major advance in physics came from anomalies: Mercury's orbit, blackbody radiation, the photoelectric effect. There is currently no anomaly that demands simulation. This is the strongest argument against overemphasizing it. Physics follows necessity, not novelty. Now consider limits of knowledge. Gödel's incompleteness theorems show that any sufficiently complex formal system contains truths it cannot prove. If the universe is a formal system, it may contain facts that cannot be derived from within. Simulation could be one of those facts. But again, physics cannot access it. The universe does not behave like a dream. It behaves like a system. Whether that system is fundamental or implemented does not affect its operation. What matters is that it obeys rules, and those rules are discoverable. That is why science works. And that is why the simulation question, while fascinating, remains secondary to the task physics has always had. If you found this explanation helpful, consider subscribing to Science Sleep for more calm, evidence-based explorations of physics, cosmology, and the nature of reality. New videos go deeper into the questions modern science can answer, and the ones it can't. And if you have thoughts about whether the universe could be a simulation, leave a comment below. Your perspective is part of the discussion.